Okay, hello and welcome everybody to today's ISGC seminar. Today's speaker is Pau Amaro Seoane. He did his PhD in 2004 at the University of Heidelberg, and then he did his habilitation in 2016 at the University of Potsdam. And currently is a professor at the Department of Applied Mathematics at the University of Valencia. Thank you very much for agreeing to giving this talk. And with that, I hand over to you. The stage is yours.
Thanks, Robin. So first of all, let me apologize to all of you if you hear a lot of background noise, because I am right now in an airport. I was not planning on doing this in an airport, but such is life. So if you have any question at any point, just ask me, because this is the only way of making this something fun, at least for me. Otherwise, I'm just staring at, at myself and a monitor in front of me. Anyway, I have tried to prepare something as general as possible and to cover as many aspects as well as possible. So this is going to be extremely hand-wavy. We can go deep in details if you want, but maybe we can postpone that for the questions. So I've called this a cartography of space-time around supermassive black holes with extreme mass reduction spirals. I don't care if we cover all of the slides or not. The most important thing for me is that you get the message of this talk about how many things you can do with gravitational waves from a particular source. Gravitational waves, as you know, are very much in fashion now because we are observing them. But for many decades, they were considered as something hypothetical. We had a theory, but we did not have the data, which was a situation very similar with cosmology before Kobe, right? They used to call the cosmology a data-starving science until the first data arrived. And the same has happened with gravitational wave physics, astronomy, whatever you want to call it. In any case, I'm going to talk about something very particular, which is the capture of a compact object, a small compact object, by a supermassive black hole. These are my hands, and this is why it's going to be a hand-wavy talk. So the main idea is the following. You want to have a supermassive black hole with a mass of about 10 to the 6 solar masses. Why? I can explain. And a small compact object with a mass of typically 10 solar masses. These two things are going to form a binary, and because you have a binary, you have a quadrupole, and if you have a quadrupole, you have emission gravitational radiation. Now, the particularities of this problem are such that they make this one of the most interesting sources of gravitational wave of the gravitational waves, in my opinion. Anyway, let me just flash you, and I mean it like that, to flash you some slides. Just to give you some context, when you talk about high energy phenomena and astrophysics, you refer, about accretion and these kind of things. But real high energy comes in the fashion of gravitational radiation. Look at these numbers. So this is Kip Thorne, when he was giving the press announcement, release, or whatever interview about the first detection of 2 weak sources. The first source, sorry about the background noise, we have a big group of Germans drinking beer here. The first gravitational wave source detected was GW150914, and this had 2 light masses. These were 2 black holes of masses about 40 and 40. Now, the total power output, if you calculate that, Kip actually mentions that in the press release, the total power output of this first source is greater than 50 times all of the stars in the whole universe put together. And this is no exaggeration. This is like that. Now, there is one catch here. We're talking about power. Power means that you are dividing energy by time. And the total duration was of 20 milliseconds. And therefore, you get this impressive number, 50 times all of the stars in the whole universe put together. That's how much energy, power was released. Now, if you want to translate that into energy, you will find out that the energy released after the merger of these first gravitational waves corresponded to only, in quotation marks, as you can see in the slide, to 3 suns being put completely into energy. E equals mc squared, you know that? So you take 3 suns, you put them into energy, and this is how much energy was released. This was merged at about 480 megaparsecs, millions of parsecs, right? A parsec is about 3.3 light years. So this was merged when life here on Earth was starting at a molecular level, which is impressive. So I said molecular cell level. Now, these 2 sources had a mass of about 40 and 40. If you move on to real powerful sources, so supermassive black holes and not stellar mass black holes, then we're talking about sources, say, for instance, of just to give you a big number, 100 million solar masses. Consider 2, so a binary made out of 2 supermassive black holes of masses 100 million and 100 million. Well, that corresponds to putting completely into energy 5 million of suns. So this is a big perturbation of space-time. You know that gravitational waves are basically a perturbation which propagates following a wave equation, which has some peculiarities, but I will not talk about them now. This is the way these things, propagate through space-time, and this is the way we can measure them and extract a lot of information. The same way you use your, cell phone to get pictures and messages for your friends. With radio waves, with gravitational waves, you can get information from regimes which are completely inaccessible to light, to the photon, which is our oldest friend in astronomy. Anyway, black holes. So let me just give you, so the main idea, I mean, don't look at the slides because they're boring. But the main idea here is that black holes are very interesting. They are fundamental, looks like they are fundamental, and they're very, very simple. Contrary to what one imagines, black holes are extremely simple. You can completely describe a black hole with 2 numbers, actually 3, which are the spin, so how much it rotates, its mass, and if you want, charge. But probably astrophysical black holes do not have charge. So we're talking about completely describing this very interesting objects with 2 numbers. Imagine of trying to describe one hair, one human hair with 2 numbers. You cannot do that. You need millions of numbers. So black holes are actually very simple, but we don't know much about them. We know that there are stellar mass black holes with masses between, say, 5 and a few tenths of solar masses, and we call them stellar mass black holes. In principle, they are everywhere in the galaxy. We have supermassive black holes, probably, and they are very fashionable. They show up in basically a lot of Hollywood movies. So they are very attractive and interesting. They have masses between 10 to the 5 and 10 to the 10. 10 to the 10 is 10,000 million solar masses. And then you find them in galactic nuclei. And if on the one hand you observe, an adult, and on the other extreme of the distribution you observe a baby, it stands to reason that in between you should have, a teenager. So something in between should exist, and we call them intermediate mass black holes with masses between 10 to the 2 and 10 to the 5. But this is still hypothetical, although the last results by LIGO indicate or seem to indicate that these things actually exist. Anyway, what do we know about black holes? Have you asked your question this question? Well, first of all, is that general relativity predicts their existence. Second, because we have the similarity theorem, we talk about trapped surfaces, and we have a long list of physical phenomena that can be only explained with black holes. We have a long list of indirect observable indications, we have probably an even longer list of theoretical motivations to believe, in quotation marks, that they should exist. This is actually a very common situation in science where you have long lists to, have a strong, at least belief that something should exist. Now, the question is, and this is not just, does not only belong to astrophysics or physics, this is a situation that you constantly face in other areas of any kind of science that you can think of, biology, chemistry, etc. So why do you need such long lists? I'm talking about a long list of indirect observation implications and a long list of theoretical motivations. Why do you need such a long list? Well, because you do not have a direct evidence. If you only have one very strong evidence that black holes exist, that would mean that everything is fine, right? You don't need to explain with a very long list that what you observe with one evidence. So it looks like we do have one direct evidence. I said that we do not have one direct evidence, but it looks like we have one of them. Look at this. This is the first detection of the gravitational wave. Here you have the strain, which is basically how much you can stretch or expand the arm of the arm length of your detector divided by the length of the detector. So you are measuring parts of 10 to the minus 21 in your available length, which in the case of LIGO is of about a few kilometers. And over here in the x-axis, you have time seconds. So this corresponds to the first detection of LIGO. Now, over here, this first part of the evolution is what you call the spiral. Over here, you have the early measure and bring down, and these last little tiny bits by the end of the evolution is where the so-called quasi-normal modes should be hidden. And if you detect the quasi-normal modes, then you know for sure that the thing that you're talking about is a black hole and nothing else but a black hole, at least a general relativity if you want a spinning black hole. Now, the problem is that with LIGO, as I told you, we're getting nanoseconds of data. And the signal to noise ratio that you get for all of this signal is of about, this was one of the loudest, and the total signal to noise ratio that we got was about 24, if I am not wrong. Now, if you want to extract here the quasi-normal modes, you would need at least a signal to noise ratio of about hundreds. And we don't have sources with signal to noise ratios of hundreds. We have detections with signal to noise ratios of 20, etc. So it looks like right now with LIGO and LIGO, we cannot say much about black holes. I must note, however, that there has been some very interesting and attractive work by Badri Krishnan about extracting quasi-normal modes from these last bits of data. And in their papers, Krishnan and his collaborators show evidence that some of the quasi-normal modes could be here and could have been already been detected. So please check his papers because they are very interesting. In any case, so these waves are a proof for the existence of black holes, right? Well, as I have just said, by the way, I don't like the word proof because proof is something that you reserve for mathematics. I should have written here something like evidence, right? So what I'm trying to say is that what you see here in this slide is not an evidence for the existence of stellar mass black holes. As a matter of fact, there have been, right after the detection, a bunch of people, actually at least two, these Victor Cardoso and collaborators, but also Cecilia Querenti and collaborators, the two of them did the following exercise. You take this wave and you try to reproduce it with an exotic object. In the case of the paper, the work by Victor Cardoso, this is a wonderful paper, with Francine and Pani, they exactly reproduced the wave. When I say exactly, it's within some error, of course, but it was basically the same thing. they reproduced the first detection with two wormholes. Cecilia Chiarenti with Luciano Rezzola, also two friends of mine, they did the same exercise with a gravastar. A gravastar is something, it's a very strange star, which I will not describe now because we don't have time, but the point is that it has, it has a surface, so it's not a black hole. So the point is that with LIGO and Virgo, we're still far away from stating this thing that we just detected is a black hole and nothing else but a black hole. This paper by Berti, which is also a good friend of mine, with Barause, also Cardoso, and Chris Wilczynski, who unfortunately passed away recently. I think 2 years ago. They published this paper stating what I am telling you. I want to probably have to wait for spaceborne observatories like LISA in Europe, ESA and NASA to look for these crazy anomalies. So, oh, by the way, a little bit of propaganda. Allow me to say mention very briefly that in 2015, but that it was presented in a series of meetings and workshops well before 2015. A very good friend of mine, a dear friend of mine, Shen and me, we predicted the characteristics that black hole detections by LIGO and Virgo should have. They should have masses between 30 and 100, typically, low spin values, and basically be eccentric. The first detection was exactly that. So it corresponded to two black holes with masses of 40 and 32, basically, at low spin values, although I am cheating here. If you look close enough, you will see that this is 0.31 plus 0.48 minus 0.28, and 0.46 plus 0.48 minus 0.43. But anyway, they claim, the LIGO collaboration, claim to be able to tell apart the different spins, and it looks like they are very mild, always below 0.5. Anyway, nowadays, most detections follow our prediction, which is between this merger here up to larger masses. So it is like about 90% of all detections by LIGO and Virgo are following our prediction. But anyway, enough propaganda. So why is this so important? From the point of view of fundamental physics, what I just showed to you means that LIGO, so the LIGO and Virgo detections of mergers and the spiral of neutron stars are a prediction of general relativity in the strong regime, because it's a very long way of saying general relativity seems to be correct. Number two, we have a proof, again, I don't like the word evidence, a very strong evidence that gravitational waves exist and that out there in the universe, objects consistent with the general relativity stellar mass black holes are present. Again, this is a long way of saying gravitational waves are there, and it looks like a stellar mass black hole should be there too. Now, from the point of view of astrophysics, the following statements seem much more, how would I say, modest, but they are very important. One, we now know that these dark objects, I'm going to call them black holes now, exist, and they have masses larger than the nominal 10 solar masses. Why do I say nominal 10 solar masses? I say nominal 10 solar masses because from a point of view of stellar evolution, we don't know how to create a black hole with a mass larger than 10 solar masses. Of course, you will find papers published about the formation of black holes via stellar evolution with masses larger than that, but I have my strong doubts about them. In particular, because here we're talking about, when you talk about a binary, and you have to combine that with a stellar evolution, things get extremely obscure. So mass transfer, for instance, between one object and the other object is, for me at least, something like a black box, which I do not understand at all. Anyway, there are people who claim to understand it, but I don't understand their works. Now, point number two, these dark objects, these black holes, form binaries, and they merge. We had indications that this was the case via X-ray observations, but now we know. So what about supermassive black holes? Do they exist? Well, if you look at the galactic nuclei, it looks like we are seeing things which look like black holes. For instance, if you have seen the Event Horizon Telescope observations, this is M87. This is actually taken from XKCD. If you don't know XKCD, I highly recommend that to you because it's very fun and accurate. And this plot, as usual, usually these things, you have this text alongside which says not to scale. Well, this one is to scale. And this is the dark thing that you observe in M87. I don't want to call it a shade, sorry, a shadow, they call that, because it's confusing. But you see something black here. It's confusing for me, not for them, of course. You see something obscure here, something dark, and that would correspond to the supermassive black hole located in M87. So this is the solar system, this is Pluto, this is the Sun, and this is the Jupiter 1. This is the farthest away that the mankind has ever made. So the whole solar system fits in that supermassive black hole that you can find in M87. Now, I must say that I like very much all of the colors that you can find in this Event Horizon Telescope plots. For me, the most appealing piece of information is what you can do with astrometry at the galactic center. When you look at the galactic center, something very strange happens. There is a well, you know that the Nobel Prize in 2020 went to three people. Two of them are doing observations. I can cancel in Europe and Andrea Goetz in the US. They have been doing observations about the galactic center. And the third person was Roger Penrose, who was for his theoretical contribution to the field. But I'm talking now about the observations theory. It's very important. It's amazing. It allows you to understand things. But we are physicists, and we rely 100% on data, right? If you don't understand the data, it doesn't matter how evolved your theoretical model is. It does not matter. What matters is the data that we have at your disposition. For that, you need astronomers. You need astronomy. And astronomers have been looking at the galactic center for over more than 2 decades, and they have found out something very strange. When you look at our galactic center, it turns out that there's a bunch of stars, which, first of all, they should not be there. We don't understand why they are there. They are too young, etc. I don't want to go into details, but it is a problem per se. But they are doing something strange. They are moving. Stars don't move, at least not on a human time scale. Orion, the constellation of Orion will be there in 5 years, 10 years. It will be there when I die. It will be there when you die, all of you. But when you look at the galactic center, there's a bunch of stars which are constantly moving on time scales as short as months. And when you recover information, because you have the orbits, at least you have a full orbit for one of them, which we call S2, at the other side of the ocean, they call it SO2, but it's the same star. We have 2 revolutions of this star, and the other stars are also revolving around that point. And when you reconstruct the orbits, because you know Kepler's orbits, you have to correct a little bit of relativistic effects, not that much, but you can reconstruct the orbit. And when you do that, it turns out that there is something around, there's something at the middle of this bunch of stars, these S stars, which has a mass of about 4 million suns, actually 4.3 solar masses, enclosed in a radius of about 22 millions of kilometers. This sounds like a very large distance. It is not. From the point of view of a galaxy, this is a microscopic distance. So it's about 1/3 the distance between Earth and Sun. Now, this very much looks like a general relativity supermassive black hole. There is some room for, because for errors, but it looks very much like a supermassive black hole. But in reality, all of the information that we have is that there is a very deep potential well over there, and the stars are moving around it. So we don't know anything about its nature. We cannot run, no-Hale theorem tests, etc., because we are still too far away. Now, all of this long introduction that I have given to you, is already 2:30, is for the following. What I wanted to do was to convey you the message that it is extremely difficult to work with light. And don't get me wrong, these people are not idiots. This is an extremely difficult exercise. I mean, they got a Nobel Prize for this. We are on the plane of the galaxy, so we're looking at the galactic center from the edge, and we have billions of stars in front of us. We have gas, we have dust, and nevertheless, these people have managed to get to a distance so small as 1/3 the distance between Earth and the Sun, and to resolve what is in there. So this is impressive. But it is really hard to work with light. Light gets scattered, light gets absorbed, etc. Light decays as 1 divided by r squared, because we're counting photons, and you know that the farther away you move, the fastest it decays as 1 divided by r squared. Now, when you work with gravitational waves, things change dramatically. Why is that? That's because, gravitational waves, as I said at the beginning, are a perturbation of space-time. So it is you and me, and now, what is perturbed. So basically, and there is a lot of information hidden in this basically, they don't get scattered or absorbed. But I will not say anything about that. I will just mention that I am cheating a little bit right now. So that perturbation, which is a perturbation on space-time, meaning you and me, and now, and at this time, that perturbation can propagate as much as it wants. It's a wave, right? And that wave decays as 1 divided by r. And that's because we are catching the full front of the wave. So it decays as 1 divided by r. Electromagnetic waves also decay as 1 divided by r, but we're counting photons. Here we're just getting the whole wave. Now, let's go back to the very beginning when I started talking about this subject. We're talking about the capture, so the gravitational wave capture of a small compact object with a mass of 10 solar masses by a supermassive black hole. And for that, I want to give you a very short introduction about what I'm going to say now. First of all, the small object is going to revolve. You should look at my hands. I don't know whether you can see them, but don't look at the slide. Probably I could just go like this. I could stop share so that you can see. So on the one hand, you have a supermassive black hole with a mass of about 10 to the 6 solar masses, and over here you have a small compact object. Now, this compact object starts with a very high eccentricity, and I don't have time to explain why, but this is the case. But it's not going to move along a Keplerian orbit. Why is that? Well, because of a few things. First of all, we have gravitational radiation, which means that we have energy loss. If you have a binary and you lose mass, the symmetry axis is going to shrink, right? You know that. This is the same thing in the same way that our satellite going around the Earth will suffer friction and then will decay. This system is losing energy, so that the small compact object is going to approach the supermassive black hole. On the other hand, we have relativistic precession. You know that for Mercury, right? And that you don't know to need the general relativity, special restrictive relativity is enough to understand that. We have precession. And on the other hand, if the central supermassive black hole has a spin, then space-time around it is going to be dragged. This is the lens-steering effect or the frame-dragging effect, which means that conceptually, if the supermassive black hole is spinning, the space-time around it is going to be twisted. And the orbital plane is going to change, which means that if initially this was the plane of the orbit, and after a while it has basculated to a different, say, inclination with respect to the first plane, The compact object, which is very far away, will arrive to the orbital plane. It will see a different space-time, and therefore it will change its orbit. When it comes back after reaching epicenter, spin might have changed again the plane of the orbit, so that the inclination will be different, and again, and again, and again. So you have a source which is basculating. It's going from, it's exploring basically almost all kinds of inclinations. And as a result, we have the following. We have a small compact object, which is a swimming distance, is a precession, and the orbital plane is basculated, which means that, well, as a matter of fact, it's like having a camera taking pictures of a space-time around a supermassive black hole here. How many pictures do you have? It's about the mass ratio that you have. This is not strictly true, but it's approximately true. So you have a mass ratio, you have a 10 to the 6 here, you have a small compact object with a mass of 10, you have a mass ratio of 10 to the 5, which means that you have 100,000 pictures of a space-time before the smaller compact object crosses the event horizon and it's gone for good. Now, this is a little bit, and this is why I named this talk a cartography of a space-time. This is a little bit what sailors in the past used to do. They would, sail across the coast and try to draw what the coast looked like. Now, we have a probe that is sending us very precise information about the geometry of a space-time around a supermassive black hole. Now, let me share again this thing here and go back to the slides. So, all of this, why should be interesting? Is it interesting only in quotation marks because we're going to get information about the warped space-time around supermassive black holes? No. This is interesting because you are combining, as I said before, astrometry, well, anything related to astronomy, astrophysics, if you make a distinction about the two of them, which I don't, fundamental physics, and even mathematics. Black holes are something very strange. Even if they are very easy to understand and to describe, they are very strange. They are something that we don't understand. And even if general relativity is accurate enough, or let's say, I'm actually stealing the words of a very good friend of mine, Leo Barak, here. General relativity is a very honest theory. It tells you exactly where it breaks down. And general relativity breaks down at a point or moment that we call singularity. So singularities are something as to, it's like 0 candies divided by 0 children. You have 0 candies, and you have 0 children. How many candies do you give to every children? I don't know. And the same happens when you get to a singularity. What happens at a singularity? No, I don't know. And by the way, a singularity can be a moment, if your black hole is not rotating, or a place, if it is rotating. But in any case, why are singularities interesting? Well, they're interesting, first of all, because this is the place where our best theory of gravity breaks down. And relativity is amazing, it's wonderful, but it's a theory. And theories break down. And that's the fun thing about physics, right? We have to replace always a theory by a better one. And this is the place where everything just, goes completely wrong. Now, let's talk about roll lines. A singularity, if you're talking about a Schwarzschild black hole, so something that is not rotating, a singularity is not a point in space-time where gravity becomes infinite. You listen and read this thing everywhere in the internet, and actually by many, unfortunately, senior researchers, but this is not true. When they tell you a singularity is a point of infinite density and mass, well, that's forget about that. That's not correct. A singularity is something much more subtle. A space-time, like our space-time, is singular if you cannot extend it, which means that you cannot embed it as an open set of a strictly large spacetime. This is a very convoluted way of saying that your real line, so if this is your life, this is time, right? And you are this particle, you are born here, and you will die here. Now, this space-time where you live is going to be singular if you cannot extend it. What does it mean? It means that it cannot be contained by another variety which is larger. And last, this is not the only condition, there is a second condition. It admits a causal curve which has either a fine past, you were born on the 28th of March 1983, I don't know, or a fine future, you will die on the 21st of February, if you want, of 2082, or both things. Okay, so if your life is causal, you have a fine past and a fine future for the two things, then your space-time is going to have a singularity. Now, singular space-times. It's not only the universe, the Big Bang is a singularity. It's a different kind of singularity, but anyways, a similar singularity. Especially black holes have singularities. Every future extension of a particle falling, like for instance, if you fall into a black hole, a supermassive black hole, and please make sure that you choose a very large supermassive black hole, because otherwise we're going to have problems. Every future extension of a particle falling inside the event horizon reaches the singularity in a finite time. And please note that the singularity is a moment, it's not a place, it's a moment. So if you cross the event horizon of a supermassive black hole, you will reach an infinite curvature, and at the end of this same time at a given moment. Also, can talk about cosmology with Freeman, Lemaitre, Robertson, Walker spacetimes. I will not go into details, but this is, by the way, the proper definition of the Big Bang. There's a finite past, and there's a anyway, I don't want to get into this. So how do you interpret singularities? Well, it's not clear. We don't know. Because again, how do you interpret 0 candies divided by 0 children? You don't know how to interpret this. It does not make sense to ask this question. The interpretation of incomplete wave lines is not clear. An observer with a causal curve which is incomplete would have a fine past or a fine future, or the two things. So what happens beyond that? So what happened before the Big Bang? What happens when you reach the singularity within, in the inside of a black hole? That's well, a free question without an answer. Actually, doesn't make sense to ask that question from our point of view. Anyway, all of this is to tell you that this is not an academic exercise, and there is a direct link between what I have explained to you before and the singularities. Penrose and Hawking, you know this, they used different techniques with the differential topology and inversional calculus to link the presence of singularities, the real, this is really not an academic exercise, this is something that happens in our universe, to link singularities with event horizons. And it turns out that, anyway, I'm going to skip all of this because I don't want to mess you even more than I am already. But the point is that if you have an event horizon, you must have a singularity, and you can link the two. If your black hole is rotating, your singularity is going to be a time, a space-like singularity, and it's going to have the shape of a ring. If your black hole is not rotating, Schwarzschild, your singularity is going to be time-like, and it is, so to say, well-behaved and nice. But in any case, it is something that really deserves attention and study, because if we want to understand what gravity is, we must do better than general relativity. Okay? By the way, there is a connection between geometry and topology. you know that the integral of the curvature of a manifold is 2 times pi, the Euler characteristic. For instance, on a plane, the sum of the angles of a triangle is 180 degrees. So you can link, thanks to the Gauss-Bonnet theorem, topology and geometry. So in principle, you can get information about the topology of your space-time outside of the black hole via the extraction of the information that you have in geometry. There is one point with this, namely that the Gauss-Bonnet theorem is for 2 dimensions, and we need 3 dimensions here. There are extensions of 4 dimensions, etc., but we need 3 dimensions, and the extension is not true. Anyway, so extreme masters in spirals. Let me show to you a video, and actually we're getting close to the end of this presentation, but let me show a video with actually the sound. So please watch out, because I don't want to blow up your ear. So let me see their screen and basic advanced share sound video and there cancel. Well, I don't know whether you want to hear this. You tell me if you hear it. Wait a second. Can you hear it? Yes, no. Setting. Yes. So what you can see here is a black hole. This is a video performed. So this video was done by Steve Glasgow from the Max Planck Institute, a good friend of mine, many years ago. But it's still a very good video. You can find it on YouTube, I think. So you have here a black hole with a mass of 3 million solar masses, and a small compact object with a mass of 90 solar masses. I don't like the choice of this mass, but well, it's good enough for an illustration. Here you have the Planck form, and every single of these peaks corresponds to a burst of gravitational, a strong burst of gravitational radiation, because a small compact object has reached the periapice of the supermassive black hole. The red line corresponds to a trace duration of about 1 day. As you can see, you don't see here, Keplerian ellipses. The plane is basculating, the symmetry axis is shrinking, and you have precession. And if you can hear the sound, which I don't know, there are bursts of noise, because Steve increased the frequency so that you can hear it. So this is about I cannot see it. Okay, it's about 756 days before the measure, and the relative velocity is 20% the speed of light. Let's jump forward 650 days. Now, this is about 1 year before the merger. Speed has gone up to 27% the speed of light, and the structure of this wave, this polarization, which is the plus polarization, becomes more and more complex, which is very interesting, because you will have more information contained here, but it's going to be also more and more complicated to extract. Now, every single of these peaks is what currently LIGO is detecting. We're not going to get one peak. We're going to get, as I was saying before, about 10 to the 5 peaks. So this is going to take months, if not years. So we have years of coherent data from a single shot. You hear how the frequency is going up. So it's we say in gravitational wave astronomy, we say that the mass is chirping, it's going up, it's pitching up, it's going like, right? We will start to see around here how resonances form, This is because in this problem we have three different fundamental frequencies. And whenever you have a particular combination of the three of them, you build up these resonances. You will see here very nice geometrical figures forming, which contain a lot of information. Like this one, for instance, you can see that it is clear resonance. And by the way, look at the structure of the waveform. This is both impressive and also a nightmare. It is impressive because here you have a lot of information, but it is a nightmare because people doing data analysis, the hard work, and extremely challenging. This is extremely challenging work. So I'm going to have to fit this somehow. And believe me, you must be extremely smart and resourceful in order to fit in here a waveform. We actually currently don't know how to do it, but we have to do it. This per se is really, our research field, and requires really the brightest minds because, first of all, one, at these mass pressures of about 10 to 10 to the 5, we don't know how to produce this kind of waveforms. And second, if you try to fit this, we don't know how to do it. Even if we had, well, of course, if we had a perfect waveform to do this, probably we would be able to do that. But currently, it is just impossible to do it, not even using, brute force with supercomputers. We cannot do this. We don't know how to do this. We need another model, like if you remember Franz Pretorius in 2005, we need a very smart person with a completely new idea who is able to address this, to solve the problem. Not just to solve the problem, but to also to understand how do you solve the problem. This is probably doable via a very, very credible, doable via cell force, but a cell force is extremely complicated. One month before the merger, you see how you are covering all of your phase space, basically, and look at the complication of the waveform. And you're going to ask yourself, what is going to happen when you hit here 0 days? Well, what is going to happen is that you're going to have silence. And why do you have silence? Well, we have silence because the thing has crossed the event horizon, and you cannot hit, you cannot get any kind of information. Let me go back briefly. Let me go back to the presentation. Here, view presentation, and there are many options here. There are the open this area. So
Paul, you're muted.
yes, sorry, I was dragging the bar and I muted myself. I was saying that you have an illustration here. You can check this in this review article of 2021, but it's basically what I said. But anyway, so stream masters and spirals. This seems to be like a very strong statement, but it's completely true. There has not been any other mission conceived ever in the history of mankind, planned or even thought of, that can do the kind of science that you can do with the stream masters and spirals. General relativity, again, is a theory and it means cooperation. And we are talking about a unique probe in a strong routine. The real line of stream masters and spirals, I'm going to give you a geodesic of a spacetime, geo quotation marks because geo refers to Earth, but nevertheless. We're going to have probes of the geometry of spacetime around those black holes, dark objects, so that you can test alternative theories of gravity if you wish, although I am completely fine with standard boring quotation marks relativity is already challenging enough, but a lot of people are testing alternative theories. Well, you are going to be able to test them and rule them out very likely, I hope. And from the point of view of astrophysics, you can measure redshifted parameters such as the mass of the supermassive black hole and the spin with extremely low errors. So small that they are ridiculous. For instance, you can measure the redshifted mass with an error between 1 and 0.1%, and the spin between 0.1 and 0.01%, being pessimistic. Actually, these numbers can go down by a lot, but I don't want to talk about that. And the most interesting thing is that these measurements are a direct reading. And please pay attention to my words. These are a direct reading. You don't need to do any modeling. The only thing that you are assuming here is that general relativity is correct. If you go and talk to your friends doing X-ray astronomy, I have many of them, they will get a heart attack because they must rely on a number of, a lot of modeling because, as I said before, it is very hard to work with electromagnetic radiation. Okay. So, and just to finish this, can we detect them? It looks like that. We have this experiment called LISA, which is going to be the first dedicated space-based gravitational wave detector. ESA and NASA are paying for this. It's mostly ESA. We have 3 spacecrafts. This is just an illustration, but the point is that in every single of these spacecraft, we have free falling mass towards Earth. So this thing is, think about that, and this is why I said at the beginning that it is important to understand the experiment. I personally always try to understand both the theory and the experiments, the data, because if you don't do that, you're lost. And what these people are doing, and I say these people because I am not involved with the technology, is really, breathtaking. You have a satellite which is harboring a test mass in the shape of a cube on free fall towards Earth, and you are constantly measuring the distances between the 3 cubes. So de facto, by the way, you have here 2 interferometers, not just 1. And the length of the arm is of 2.5 million kilometers, and you need a resolution of, please pay attention, 1 picometer on those 2.5 million kilometers. And what's the worst, you cannot touch the cube. Again, in each of these satellites, you have a free-flowing cube towards Earth. But you cannot perturb that motion. You cannot perturb that geodesic. Because if you perturb it, your measurement is going to be wrong. So you have to protect this free-falling mass with a satellite, which is going to shield it against the sun. But on the other hand, you are charging it with cosmic rays. So you have to decharge it. And ask yourself the question, how do you decharge a mass without touching it? So these kind of things is what make the experience so challenging. So in that case, in June 20th, 2017, LISA received the clearance goal from ESA. And a bit later, NASA decided to participate with a minor contribution. This is mostly ESA. And they required that we, in quotation marks, we show that we can do that. So on this, so we had this experiment called LISA Pathfinder, which was a technology, a technology mission to prove actually that we can do this. And they proved in an impressive way that we can do that. This is differential acceleration, so meters per second squared in some kind of units, divided by hertz to the power of 1/2. And this is frequency. So this is what ESA here was requiring. Well, in blue, we have what these people managed to do after launch, a few months after launch in 2016. Sorry, this was right after launch, the blue curve. So well below the requirements. And a few months later, February 2017, depending on the range of frequency that you're talking about, they were about 2 orders of magnitude, so a factor of 100. They managed to do this a factor of 100 better than required. So this was impressive. By the way, you are doing here sub-femto G experiments, which is impressive. Anyway, so I probably should stop here because I have been talking a lot and saying too many things. I could go on and on for another 1 or 2 hours, but it's probably best that I stop now and listen to you if you have any questions, because nobody asked anything so far. So I'll stop here.
Thank you, Paul, for this really nice talk. Are there any questions in the audience?
I have
Did you
one.
understand everything? Go ahead.
Can I ask one question?
Yeah, sure.
So you showed an animation in which you have the resonance stage for the small particle. So my question is that is it true that the small particle always pass through resonance stage irrespective of the initial condition of the small particle?
As I said, so the nice thing about this is that it is a very well-posed problem, at least in the regime. Once you have the couple from the astrophysical regime, when you are in the two-body regime, at these small distances, these are very well-posed problem. And you have 3 fundamental frequencies. So the answer is yes, you're going to always have this kind of resonances. You should check the work of Anna Flanagan in the early days, with also Steve Drasko, Scott Hughes, and these days it's mostly Beatrice who is working on this. And yes, the resonances are there, and there will be, if you talk to data analysis people, they will be crucial at the, when you want to extract parameters.
Oh, okay. Because if I understand correctly, for example, if you count the volume in the phase space, the resonant region is very, very small.
That's true.
Okay.
Well, it's a small, but take into account what is a small here. Are the detections of LIGO and Virgo short for you? Are they small? The answer is probably yes, or not. It depends. They are giving you, they provide you with a lot of information. Here we're talking about months of data, and fraction of those months, weeks maybe, I don't know, are going to be in, or at least days, are going to be in resonances. So that's not a small.
I see. Thank you.
Are there any other questions?
I have many questions.
Okay, maybe I have one question. I mean, there are some black hole spacetimes which have these so-called conical singularities, which are different from what we usually refer as the more classical curvature singularities. Do you have an idea how one could maybe interpret this physically? I mean, I have an idea how I would interpret it, but maybe you have a different one.
But what is the question?
So they're like space-time, for example, like the symmetric, where you have on the axis a conical singularity, which is simply that the space-time just kind of deformed such that on these points, basically, we would connect it such that it is like the tip of a cone. And I guess it's, of course, also a failure of the description of the space-time itself. But the question is, of course, how we really would interpret this physically.
I mean, you need some context, right? So conical spacetimes are very interesting solutions of general relativity, and you often use them for to study or model certain types of topological defects, like for instance, you're referring to cosmic strings. I don't know. In any case, these spacetimes have very unique properties because of their geometric structure, which is very different from what you expect of conventional spacetime models. So, but you know that a conical spacetime, I guess is what you're talking about, can be interpreted as a kind of, well, flat dimensional plane with a wedge removed and the edges of the wedge identified. This is interesting, but I am much more down to earth. Anyway, of course it is interesting and I should be addressed, but the dissimilarities in conical spacetimes, they require discontinuity in the, sorry, a lot of people here. And I am losing the thread. So they require discontinuity in the angular coordinate, right, theta. And this results in a curvature singularity at r equals 0, which is different from the much more familiar singularities found in, say, black hole solutions where you have at a given distance that singularity. So the conical singularity, I don't know whether this is what you're talking about, it's not a curvature singularity in traditional sense, but it is a topological singularity. For the curvature is concentrated, if you want, at a single point. This is well beyond of what I would hope to achieve with the data that we're going to get with Lisa. But in any case, the way to go for me is very well defined, and it is one step at a time, doing baby steps and trying to understand first, you know, if you want orthodox dual post relativistic gravity, and beyond that, it's just a matter of time and data, I insist. I don't know whether this is giving you any kind of information, but
my problem is I don't really know how to exactly precisely describe it. Maybe it would be easier if I had a blackboard and to draw it there.
okay, Louise
I mean,
wants to protest or say something.
well,
Thanks. I just had a question. Can you elaborate on why is it complicated to come up with a waveform for the EMR?
It is not complicated. It is right now it is impossible, and that's because of the mass ratio. You see, when you're talking about mass ratios of about the same, so mass ratio of about 1 so you have here 10 and 10 solar masses, a black hole of 10 solar masses and a black hole of 10 solar masses, or 10, 20, or a million to million, everything is fine. But as soon as you start to make the mass ratio much more different, like you go to mass ratio of say 10 to the 2, 10 to the 3, 10 to the 4, you run into a very bad problem, which is the non-linearity of the field equations of gravity, so Einstein's relativity, right? And as of now, this is a problem that we don't know how to solve. So Eloise, by the way, you could ask yourself, if we don't know how to solve this, what was that thing that I was showing to you in the video? Because I said, we don't know how to do these things, but I was showing you this thing. So what I was showing to you was a kind of a patchwork. It's an approximation of an approximation, which happens to allow us to probably claim detection and extract parameters, but it's not the solution. It's not the strict solution of Einstein's field equations in this mass ratio regime.
Okay, I see better. Thanks.
Questions? If not, I would suggest maybe to end the official part here, and then if you still have time, maybe for some more free discussions. Thank you very much again for the talk. Maybe
Just coming back to me.
Yeah, it looks like I'm not able to stop